All right, here's the last part. This is where we're going to look at the shear stress in that pin at A. All right, determine the maximum average shear stress in pin A of the truss. A horizontal force of P is equal to 40 kilonewtons is applied to joint C. Each pin has a diameter of 25 millimeters and is subjected to double shear. All right, so remember before we were looking at the normal stress of the members, and the diameter that was given to us was the diameters of the members. This is the diameters of the pin happening at these joints here. And we can see this kind of side view of how it's getting double sheared. All right, so the first thing we want to do, let's go ahead and just like get that cross-sectional area out of the way. So if D is equal to 0.025 meters, I'm not going to write it all out again, but then the area will be equal to 4.909 times 10 to the negative 4 meters squared. So we'll have that ready when the time comes. And we're trying to find the average shear stress, the maximum average shear stress at pin A. And it does say right here that it's under double shear, and we'll see what that looks like when we get to the free body diagram of the pin. All right, so the forces acting on the pins at this A and B are actually just the forces, the support reactions. So this time we will go ahead and solve for those support reactions. Because it's a truss, we know that one of these vertical supports is going to be going down and one will be up. Um, Kind of this little cool coupling moment that works out. But I will just draw them in the positive for right now. But I know that this is the only horizontal support, this AX, so we'll have it going opposite this 40 kilonewtons. And just to save time, I'm not going to draw a separate FBD for this. I think you get the idea. But in practice, I mean, when you're doing it for your own, yeah, do whatever works. But it's always good to redraw everything. And we're keeping the typical coordinate system here. This being our positive quadrant. All right, so first step, we'll go ahead and find our support reactions, which will be AX, AY, and BY, because we got a pin at A and a roller at B. All right, so we have 3 equations and 3 unknowns. Works out perfectly. We can go ahead and just solve for the horizontal support reaction at A. I will write it out, but hopefully you can see what it's going to be. So we got the 40 kilonewtons in the positive direction, and I had, looked ahead and could tell that this was the horizontal reaction at A was going to be going the opposite direction. But yeah, it's also equal 40 kilonewtons. All right. So, and then if we go straight to jumping in the vertical, summing up the forces in the y direction, we'll have 2 unknowns. So let's go and sum the moments about A. And then we can just have 1 unknown in this equation, which is much nicer. All right. So BY is kind of doing this type of rotation about A. Counterclockwise, so it's going to be positive, and its perpendicular arm or whatever is 2 meters from that support at A. And then the 40 kilonewtons will be going the opposite direction clockwise, so it's going to have a negative in front, and its perpendicular direction's 1.5 meters. And then we'll go ahead and solve that for By, get 30 kilonewtons. Now we can go ahead and sum the forces in the Y direction. And you can probably see that I didn't draw AY right. It should be going this way. But that just means that when I sum these forces, this is equal to 30, that I'll get a negative value. That just means it's actually going down, or going in a different direction than what I drew it as. But I'll keep it as negative, just so we know. All right, so now we want to, well, actually, it doesn't matter if it's negative or not, because what we're looking at, we're just looking at this, I don't know if you can see it as well now, this pin at A. So our AY is still going up this way, and then our AX would be coming in and out of the page. And what we're doing, let's draw it like this. We're just going to find their resultant force. And this is just simple vector math. Oh, try it as f of a. But simple triangle math. Get that it's equal to 50 kilonewtons. So that's the total force, because those are just like the x and y components of the force of that support, and we like to break them up into those components because it's way easier to or it's almost, yeah, it's the only way really to do analysis, or the only way I know how. All right, let's do our free body diagram of that little pin, which you can see popping out here or going across right here. All right, let's change colors for fun, like purple. So our pin is this little cylinder looking thing. Here's our resultant. You know, we could come up with a coordinate system, but we're just, you know, we know that this needs to equal, the shear forces are kind of this equal but opposite, but it does say double shear. So we have it going on both sides. You can kind of see by the way it's shaped right here. But it's nice of them to tell us. So then we get that this shear force be equal to f of a, half of it, so 25 kilonewtons. And then our average shear stress at A, at that pin, is that equation. So you remember that. So be equal to 25, because we have kilonewtons. We'll want to just, like I said, keep it to newtons. It's a little easier to go down to the, you know, fundamental units, and then, you know, just go bigger from there. All right. So then we get 5.1 or 5.09 times 10 to the 7 pascals, or 50.9 megapascals.